In March 2023, OpenAI released GPT-4, and something genuinely unusual happened. The model displayed capabilities that nobody had explicitly designed or optimized for. This was not incremental improvement on known benchmarks. It was qualitatively different behavior. Consider 3 examples that crystallize the anomaly. First, physics from images. A user uploads a photograph of a physical setup, a ball on a ramp, a pendulum, blocks stacked on a table, and asks GPT-4 to predict what will happen. The model correctly reasons about forces, friction, momentum, and trajectory. It was never trained on a physics simulation task. It was trained to predict the next token. Yet something in the intersection of language understanding and visual perception produced what can only be called physical intuition. Second, code from napkin sketches. A user photographs a hand-drawn wireframe on a napkin, boxes, arrows, rough labels, and GPT-4 produces a working HTML and CSS website that faithfully implements the sketch. The model must parse handwriting, interpret spatial layout as UI hierarchy, map visual elements to code abstractions, and generate syntactically correct output. Each of these would traditionally require a separate specialized system. GPT-4 does all of them in a single forward pass. Third, and perhaps most remarkably, visual irony in memes. GPT-4 can explain why a meme is funny. This requires detecting visual content, reading overlaid text, understanding cultural context, identifying the incongruity that creates humor, and articulating it in natural language. Humor detection combines perception, world knowledge, theory of mind, and pragmatic language understanding, arguably the most integrated cognitive task humans perform. These capabilities were not listed in any training objective. They emerged. The question is, emerged from what? Microsoft Research published a 155-page paper titled Sparks of Artificial General Intelligence, arguing that GPT-4 exhibited sparks of general intelligence across mathematics, coding, vision, medicine, law, and psychology. The AI research community was sharply divided, and this debate is not merely philosophical. It determines research priorities, safety investments, and policy decisions worth hundreds of billions of dollars.
Let's look at what we actually know about GPT-4's capabilities, because the data is striking. OpenAI tested GPT-4 on a battery of professional and academic examinations designed for humans. The results were dramatic. On the uniform bar exam, GPT-4 scored at the 90th percentile, compared to GPT 3.5's approximately 10th percentile. On the LSAT, roughly the 88th percentile. GRE Verbal, 99th percentile. SAT Math, 93rd percentile. It passed the medical licensing exam, the sommelier exam, scored 4 to 5 on AP Calculus, Biology, and Chemistry. Across 34 professional exams, GPT-4 moved from below median to above 90th percentile human performance. On Massive Multitask Language Understanding, MMLU, which covers 57 subjects from algebra to virology, GPT-4 achieved 86.4% accuracy, exceeding the prior state-of-the-art by over 10 percentage points. And it demonstrated strong multilingual capability, even in low-resource languages. But here is where it gets truly interesting. GPT-4's pre-training confidence is remarkably well calibrated. When the model says it is 80% confident, it is correct approximately 80% of the time. This is a property that most neural networks lack. However, and this is critical, RLHF training degrades this calibration. After human preference tuning, the model becomes overconfident. This is a profound observation. Alignment training may compromise epistemic accuracy. There is a tension between making a model helpful and making it honest. OpenAI also demonstrated predictable scaling. They trained smaller models and used their performance to predict GPT-4's capabilities before training was complete. Loss on their internal codebase was predicted accurately from models 1,000 times smaller. The power-law scaling relationship holds even across massive jumps in compute. And on inverse scaling tasks, problems where larger models historically performed worse than smaller ones, GPT-4 reversed these trends, suggesting that sufficient scale can overcome failure modes that afflict intermediate-sized models.
Now, here is the part that should concern every researcher in this field. For the first time in a major AI capabilities paper, OpenAI disclosed almost nothing about the model itself. Architecture, not disclosed. Number of parameters, layers, attention heads, all withheld. Training data, not disclosed. Corpus composition, size, filtering criteria, temporal range, all withheld. Training compute, not disclosed. Total flops, GPU hours, hardware configuration, all withheld. Training methodology, only partially disclosed. They confirmed the use of RLHF, but provided no details on reward model architecture, preference data collection, or optimization hyperparameters. OpenAI cited the competitive landscape and the safety implications of large-scale models as justification. This represented a dramatic shift. GPT-2 disclosed everything except the dataset. GPT-3 disclosed architecture, training data, and approximate costs. GPT-4 disclosed essentially nothing except output benchmarks. The implications are significant and worth stating plainly. The research community cannot reproduce, verify, or build upon GPT-4's results. The most capable AI system in the world became a black box evaluated only by its outputs. We went from open science to closed product in 3 model generations. This is not just an academic concern. When we cannot inspect the internals of the most powerful AI systems, we cannot verify safety claims, we cannot identify failure modes before deployment, and we cannot develop the interpretability tools needed to understand what these systems are actually doing. The safety evaluations OpenAI did publish, red teaming for bioweapon synthesis, cyber attack planning, manipulation tactics, showed GPT-4 scoring approximately 60% on truthful QA, better than predecessors, but still far from reliable. A model that is wrong 40% of the time on questions specifically designed to test truthfulness is not a model we can trust in high-stakes domains.
In 2021, David Silver and co-authors, including Richard Sutton, whose bitter lesson argued that general methods leveraging computation always beat specialized approaches, proposed a radical hypothesis. Maximizing a single reward signal in a sufficiently complex environment is sufficient to give rise to all abilities associated with intelligence. This is a strong claim. It says we do not need separate modules for perception, language, social reasoning, planning, memory, or any other cognitive faculty. All of these emerge instrumentally as necessary subskills for maximizing reward in environments that are rich enough to require them. The argument is elegant. An agent maximizing reward in a complex environment must build internal models of regularities, essentially learning physics, social dynamics, and causal structure. An agent receiving high-dimensional sensory input must develop efficient perceptual representations. In environments with other agents, especially humans, an agent that can understand and generate language has a massive advantage. Theory of mind, modeling others' beliefs, desires, and intentions, becomes essential for predicting how other agents will behave. Multi-step planning emerges because reward maximization in environments with delayed consequences requires simulating future states. The biological parallel is direct. Natural selection optimizes for a single objective, reproductive fitness, in the environment of Earth. From this single objective, evolution produced eyes, ears, echolocation, language from bee dances to human speech, pack hunting, political alliances, tool use, causal inference. No separate module was designed for each capability. They all emerged because they were instrumentally useful for survival in sufficiently complex environments. If this hypothesis is correct, then the Omni model paradigm is not just an engineering convenience, it is the architecturally correct approach to building general intelligence. The question becomes not, how do we build a vision module, but what environment and reward signal will cause vision to emerge? But there is a critical caveat. The environments these models train in are not truly rich. They are static datasets, not interactive worlds. The models cannot take actions, observe consequences, and update. This may explain why emerging capabilities are impressive but inconsistent. Every large language model, including GPT-4 and every multimodal Omni model, suffers from hallucination, the generation of confident, fluent, and entirely fabricated assertions. A model might cite a paper that does not exist, invent a historical event, produce a mathematical proof with a subtle but fatal logical error, or describe the contents of an image that contradict what is actually depicted. And here is the key insight. Hallucination is not a bug to be patched. It is a structural consequence of the training objective. The core training signal is, given this context, what token is most likely to come next. This is a distributional objective. It optimizes for statistical plausibility, not for truth. A model trained on internet text, learns that after "the capital of Australia is," the token Sydney is plausible. Many people incorrectly say this, even though Canberra is correct. More precisely, the model has no internal representation of truth. It has a representation of what text looks like when humans write about things. When humans write confidently about true things and false things in similar linguistic patterns, the model learns both patterns equally well. Multimodal models have an additional source of grounding. Visual input provides correspondence between text and actual content. But hallucination takes new forms in multimodal settings. Cross-modal hallucination. The model correctly identifies an object but fabricates attributes. It sees a red car and calls it blue. Over-attribution. The model sees things that are not in the image because they are statistically associated with the context. A photo of a kitchen might cause it to describe a refrigerator even if none is visible. And here is perhaps the deepest tension in this entire field. Creativity and hallucination share the same mechanism. Generating novel text, a poem never written, a solution combining ideas in new ways, requires the model to go beyond its training data. But going beyond training data is precisely what hallucination is. Reducing hallucination through grounding, retrieval augmentation, or conservative decoding also reduces creativity. A model that never says anything it cannot verify will never generate a novel insight. This is not a problem to be solved by better training. It is a fundamental trade-off to be managed by system design.
In 2013, Segedi and colleagues demonstrated something that shook the foundations of computer vision. They showed that adding an imperceptible perturbation to an image of a panda caused a state-of-the-art neural network to classify it as a gibbon with 99.3% confidence. The perturbation was so small that humans could not distinguish the original from the adversarial image. This result was initially treated as a curiosity. A decade later, it remains fundamentally unsolved, and it has become far more concerning as models are deployed in safety-critical applications. The adversarial vulnerability reveals something deep about how neural networks learn. They learn statistical shortcuts rather than robust concepts. A model trained to classify dogs and wolves might learn to look for snow in the background. Wolves are often photographed in snowy settings, rather than learning to identify the animal itself. High accuracy on the training distribution, catastrophic failure on distribution shifts. CLIP and subsequent multimodal models showed improved robustness. On distribution-shifted benchmarks, ImageNet v2, ImageNet Sketch, ImageNet A, ObjectNet, CLIP maintained performance where supervised models degraded. The reason is intuitive. CLIP learns representations grounded in language, not just pixel statistics. If the model associates panda with both visual appearance and the semantic concept in text, pixel perturbations may not affect the language-grounded representation. But multimodal models introduce entirely new attack surfaces. Typographic attacks, placing a text label reading iPod on a banana, fools CLIP into classifying it as an iPod. The model over-relies on text cues in images. Cross-modal attacks, subtle image modifications cause errors in text generation, and most concerning of all, prompt injection, embedding hidden instructions in images or documents that cause the model to override its system prompt and follow attacker instructions. Certified defenses exist, randomized smoothing, interval-bound propagation, Lipschitz-constrained networks, but they scale poorly. The certified radii are smaller than practical attacks require, and the accuracy cost is substantial. The field is stuck in an arms race. The fundamental issue may be that robustness requires causal features rather than correlational ones, and current training does not incentivize causal learning.
Palm-E represents the most ambitious attempt to bridge the gap between language understanding and physical action. At 562 billion parameters, it combines Google's Palm language model with visual encoders and robot control interfaces. The architecture is conceptually simple, but profound in its implications. Continuous sensor data, images from cameras, joint angles from encoders, force readings from sensors, is projected into the same embedding space as language tokens. The resulting multimodal sequence is processed by the language model, which generates text that can be parsed as robot actions. A user gives a natural language instruction: move the yellow hexagon to the blue triangle. The model processes both the instruction and the visual scene and generates a sequence of actions that a robot arm executes. But here is where theory meets engineering reality, and the collision is violent. Large language models generate text through autoregressive sampling, one token at a time, each requiring a full forward pass through the network. For a 562 billion parameter model, a single forward pass takes hundreds of milliseconds on current hardware. Robot control operates on a fundamentally different timescale. Industrial robot arms require control signals at 100 to 1000 Hz, one command every 1 to 10 milliseconds. A grasping task requires continuous adjustments based on real-time force feedback. A walking robot must correct its balance within milliseconds of detecting a perturbation. Palm-E addresses this through hierarchical decomposition. The language model produces high-level plans, pick up the red block, which are executed by specialized low-level controllers operating at the required frequency. Effective, but it introduces a gap. The language model cannot react to real-time feedback within an action. The most exciting finding is in the transfer results. Capabilities learned in simulation transfer to real robots. Training on visual question answering improved robot planning. Training on robot data improved visual question answering. Larger models showed stronger positive transfer. This cross-modal, cross-task transfer is the strongest evidence for the Omni model thesis in the embodied domain. It suggests that shared representations capture something genuinely useful about the structure of the physical world. But the embodiment gap remains vast. Lab demonstrations use controlled environments with known objects, fixed lighting, and limited disturbances. Real-world deployment requires handling sensor noise, actuator imprecision, unknown object properties, and dynamic environments with other agents acting simultaneously.
As models gain capabilities across modalities, text, code, vision, robot control, the consequences of misalignment scale correspondingly. A text-only model that generates harmful content is concerning. An Omni model that can write code, control robots, and plan multi-step strategies while pursuing misaligned objectives is potentially catastrophic. RLHF, reinforcement learning from human feedback, is the dominant alignment technique. The process: generate multiple outputs, have human raters rank them, train a reward model to predict preferences, then fine-tune the language model using that reward model as a proxy for human judgment. The structural problems are well documented and severe. Human raters disagree substantially. Inter-annotator agreement on quality ratings is typically 0.6 to 0.7, moderate at best, and drops below 0.5 on nuanced tasks involving safety, helpfulness, and honesty trade-offs. The reward model is trained on noisy labels. There is a distributional mismatch. Raters are typically not domain experts. A medically incorrect but confidently worded response may receive higher ratings than a technically correct but hedged response. The reward model learns to optimize for the appearance of competence rather than actual competence. Reward hacking is observed empirically. Models learn to be excessively verbose because longer responses correlate with higher ratings. They use confident language regardless of actual certainty. They avoid controversial statements even when they are true. And then there is Goodhart's law. When a measure becomes a target, it ceases to be a good measure. Optimizing against a proxy for human values sufficiently hard will find behaviors that score high on the proxy while violating the underlying values. Anthropic's constitutional AI attempts to address this by replacing human raters with principles, a constitution, that the model uses to self-evaluate. But this introduces a recursive problem. The model is training on its own outputs, filtered through its own understanding of the principles. If that understanding is subtly misaligned, self-training amplifies the misalignment. The deepest challenge is not technical but philosophical. Human values are not formally specifiable. We cannot write down a complete, consistent, context-sensitive utility function that captures what humans actually want. Consider a simple instruction: be helpful. Helpful to whom? Helpful when? Helpful according to stated or revealed preferences. Every formalization either underdetermines or overdetermines the desired behavior.
Current Omni models are better described as broad AI than general AI. The distinction matters enormously. Broad AI exhibits competence across many domains, but with inconsistent depth and reliability. It can pass a bar exam and also fail at basic counting. It can generate sophisticated code and also produce code that compiles but gives wrong results for edge cases. It can explain quantum mechanics and also confidently state false historical facts. General AI, if it exists, would exhibit consistent, reliable competence that transfers robustly to novel situations. It would know what it knows and what it does not know. It would learn new domains as efficiently as humans. It would not be britly dependent on the distributional properties of its training data. The failure modes reveal the gap precisely. Compositional generalization. Models can answer, what is the capital of France, and what country is Paris in, but struggle with novel compositions. If the capital of France were moved to the second largest city, what would it be? This requires composing factual knowledge with counterfactual reasoning, trivial for humans, unreliable in current models. Long horizon planning. Given a complex goal requiring 20 or more sequential steps with dependencies and contingencies, current models degrade rapidly. They lose track of sub-goals, fail to backtrack, and do not maintain consistent state across long action sequences. Causal reasoning. Models learn correlations, not causes. They can report that smoking is associated with lung cancer, but cannot reason about novel interventions. Systematic counting and arithmetic. Despite passing calculus exams, models frequently fail at basic arithmetic with large numbers or counting objects in images. François Chollet's Abstraction and Reasoning Corpus, ARC, was designed specifically to test genuine generalization. Each task presents input-output grid pairs demonstrating a transformation rule, and the model must apply the rule to a new input. The rules are simple for humans: rotate, reflect, fill patterns, but require understanding abstract structure. As of 2024, the best AI systems score 30 to 40% on ARC. Average humans score above 80%. By Chollet's measure, current models are not general.
The speed of progress is itself a data point that demands serious engagement. Let me walk you through the timeline, because when you see it compressed, the trajectory becomes visceral. 2018. BERT achieves human-level language understanding on the GLUE benchmark. The community celebrates and assumes the next frontier is years away. 2020. GPT-3 demonstrates few-shot learning across NLP tasks. No fine-tuning needed, just describe the task in the prompt. This was not supposed to work this well this soon. 2021. CLIP bridges vision and language in a single representation space. DALL-E generates images from text descriptions. Separate fields begin collapsing into one. 2022. DeepMind's Gato demonstrates a single model across 604 different tasks: playing Atari, captioning images, chatting, stacking blocks with a real robot arm. Flamingo achieves few-shot multimodal learning. The specialist to generalist transition accelerates. 2023. GPT-4 passes professional exams at the 90th percentile. Palm E controls robots from natural language instructions. Google's Gemini processes text, images, audio, and video natively in a single architecture. 2024. Models begin exhibiting genuinely agentic behavior, browsing the web, writing and executing code, using tools in extended multi-step sequences. 2025. Real-time multimodal interaction becomes possible. Models that see, hear, speak, and act simultaneously. Each capability that was expected to take a decade arrived in 1 to 2 years. Now, this compression does not guarantee that general intelligence is near. The remaining gaps, compositionality, causality, robust long-horizon planning, may be qualitatively harder than everything achieved so far. They may represent a different kind of problem, one that scaling alone cannot solve. But the trajectory demands that we take the possibility seriously. We are no longer in the regime where we can comfortably say, not in our lifetime.
We began this series by asking what happens when you train one model on everything. 4 episodes later, the answer is both more impressive and more unsettling than we expected. Omni models have demonstrated a remarkable convergence: vision, language, reasoning, and action, collapsing into a single set of weights. The progression from specialist models to transformers, to CLIP, to GPT-4, to Palm E traces an unmistakable arc toward unification. But the same convergence that produces capabilities also concentrates risk. A model that can see, speak, reason, code, and control physical systems is more useful than any predecessor and more dangerous. The alignment problem scales with capability. Hallucination persists across modalities. Adversarial fragility undermines deployment in safety-critical domains. If Silver and colleagues are right that reward is enough, then we are building systems that will develop whatever cognitive abilities are instrumentally useful for their objectives, abilities we may not anticipate, may not understand, and may not be able to control. If Chollet is right that current approaches lack genuine abstraction, then we are building increasingly capable but fundamentally brittle systems that will fail in unpredictable ways as they are deployed in novel environments. Both possibilities demand the same response. We must invest in interpretability, alignment, and evaluation with the same urgency we invest in capabilities. we are scaling faster than we can interpret. The gap between what these models can do and what we understand about how they do it widens with every generation. This series ends not with answers, but with the questions that define the frontier. Is emergence real or illusory? Can alignment scale with capability? Is the reward enough? What is the cost of generality? Does a model that can do everything do nothing reliably? And perhaps most urgently, who decides? As Omni models become capable of consequential actions in the physical world, who controls them? Who is accountable when they fail? How do we govern systems whose capabilities we cannot fully enumerate? The age of Omni models is not approaching. It is here. The question is no longer whether one model can see, speak, reason, and act. The question is what it means for the world when it can, and what happens when we build one that can do things we have not yet imagined. If one model can do everything, what does everything really mean?